Before in numerical calculus, we have studied interpolation, numerical differentiation, numerical integration. A logical extension of that is ordinary differential equation. All of us are familiar with ordinary differential equations from other courses, but in numerical analysis, this is a topic we are particularly interested about. Why is it so? What are ordinary differential equations and why we are keen about it? We'll discuss that in this lecture. Let us take a function y equals e to the power 0.1 x square. This function is continuous from minus infinity to plus infinity. If I differentiate this function, then I get this y prime, that is dy dx, is equal to 0.2 x e to the power 0.1 x square. Now e to the power 0.1 x square is y, so I can write this as y prime equals 0.2 xy. This is something we call an ordinary differential equation if y is unknown and of course x is known. Now differential equation is equation that contains derivatives such as this of unknowns, and they are of two types. One is ordinary differential equation and another is partial differential equation. In this week we will talk about ordinary, and in coming week we will talk about partial differential equation. Ordinary differential equation contains single independent variable, that is in this case that is x. In partial differential equation there will be more than one independent variable, and therefore partial derivatives will appear in the equation. A typical ordinary differential equation will look like a function of x, y, dy dx, d2y dx2, etc. up to dny dxn, when n is greater than all other order of derivatives here. This kind of equation we will call an nth order ODE, that n is the highest order of derivative that appears in this equation. In this equation, x is known, independent variable, and y is unknown, dependent variable. Such an ODE is called linear in y when y and its derivative are multiplied only with constants or functions of x. A detailed discussion of when an equation can be called linear and when non-linear, we have discussed it in linear algebra part. You can go back and take a look there if you don't remember it now. In case of differential equation, just like in case of algebraic equation, unknowns cannot be multiplied by unknowns. That kind of functions we have to remove to keep the equation linear. When any that kind of functions come, it would be non-linear. The solution of ODEs are not numbers, these are functions, and there are many functions. So there is not one solution, there are many functions. So for example, we have generated this ODE y prime equals 0.2 xy from this function y equals to e to the power 0.1 x square. So y equals to e to the power 0.1 x square is a solution of this equation, but this is not the only solution of this equation. The general family of equation will be y equals 0.1 x square plus c, where this c is a constant. Based on this constant, we can get infinitely many solutions of ordinary differential equation. So uniqueness in solution will be provided by the initial condition or boundary condition in the solution, and it gives rise to initial value problem and boundary value problem in differential equation. Differential equation contains derivative, and derivative means change of one variable with respect to another. If you look at physical phenomena all around us, or the physical phenomena we study in different subjects of science and engineering, everywhere we are interested about change. When we change certain independent variable, what will be the changes in the dependent variable we want to know. Therefore, differential equations are actually the engine of engineers. This is a very useful tool for describing natural phenomena. So for instance, Newton's law of motion. It models motion of particle of mass m. Governing equation G is in such system for a particle that has mass m. The equation is m multiplied by d2x. This x is the location of the particle, that is a vector. So this is d2x dt2 equals f, that is another vector, that is force. So this is a vector equation. So essentially it has three equations in three directions. And then being a second order equation, it requires two initial conditions. One is the location at time t equals 0, that is given by x naught. And another is the velocity, that dx dt at time t equals 0, that is given by v naught. With this initial condition, we should be able to calculate the position and velocity of this particle at any given time. This simple looking equation changed the history of mankind. It tells us that the way a stone that we have thrown, they move in the same way under the same law. Earth revolves around the sun. This simple looking equation helps us to predict solar eclipse, lunar eclipse, and various astronomical phenomena. This is how differential equation changed our perspective about reality. Solution of this equation will give location of this particle as a function of time. So in this problem, we start with the initial position, initial velocity, and the parameters in this equation. Two parameters, one is mass, one is force. Then the model is our differential equation. When I give this known values at the input to the model, it tells us position and velocity as a function of time. Just like Newton's law of motion, many other laws in physics are modeled as differential equation. Most famous are Maxwell's law of electromagnetism, Schrödinger law in quantum mechanics, etc. Newton's law, when it comes to fluid mechanics, it gives rise to a very famous equation, that is Navier-Stokes equation, another differential equation. So differential equations are very important in science and engineering. As your exercise, you look around and try to find an example, try to figure out a physical phenomenon that can be modeled as an ODE. Thank you. That's all for this lecture. Happy learning.